Welcome to today's paper reading. Today's paper is titled, Mind's Eye of LLMs, Visualization of Thought Elicits Spatial Reasoning in Large Language Models. This paper was published on the AR14 preprint by Wenshan Wu and colleagues from Microsoft Research. Large language models, LLMs, have shown remarkable capabilities in language comprehension and reasoning tasks. However, their performance in spatial reasoning, a critical aspect of human cognition, has not been extensively explored. Humans possess an extraordinary ability to create mental images of unseen objects and actions, a process known as the mind's eye, which allows them to imagine the unseen world. Inspired by this cognitive capacity, the authors propose visualization of thought, VOT, prompting. VOT aims to elicit spatial reasoning in LLMs by visualizing their reasoning traces, guiding subsequent reasoning steps. The authors applied VOT to multi-hop spatial reasoning tasks, including natural language navigation, visual navigation, and visual tiling in 2D grid worlds. Experimental results showed that VOT significantly enhances the spatial reasoning abilities of LLMs. Notably, VOT outperformed existing multimodal large language models, MLLMs, in these tasks. Although VOT works remarkably well on LLMs, its ability to generate mental images to facilitate spatial reasoning resembles the mind's eye process, suggesting its potential applicability in MLMs. Figure 1 illustrates how humans enhance their spatial reasoning by creating mental images during the process. Similarly, large language models, LLMs, can create internal mental images. We propose visualization of thought, VOT, prompting to elicit the mind's eye of LLMs for spatial reasoning by visualizing their thoughts at each intermediate step. This method significantly enhances the spatial reasoning abilities of LLMs, as demonstrated in various tasks. The introduction of this paper highlights the remarkable performance of large language models, LLMs, in various language-related tasks, yet their abilities in spatial reasoning remain underexplored. Spatial reasoning is crucial for human cognition, enabling interaction with the environment through tasks requiring understanding and reasoning about spatial relationships. Inspired by human cognitive mechanisms, the paper proposes the visualization of thought, VOT, prompting method to enhance LLM's spatial reasoning capabilities. This method involves zero-shot prompting and has shown significant performance improvements in tasks requiring spatial awareness. Spatial reasoning involves understanding the relationships between objects and their movements in space. This skill is crucial for applications like navigation, robotics, and autonomous driving, where action planning relies on visual perception and spatial dimensions. While existing research has focused on the linguistic structure of spatial terms, recent advancements have shown that converting these terms to logical forms can achieve impressive results. However, this does not necessarily indicate a deep understanding of spatial information by large language models, LLMs. To accurately measure spatial awareness, tasks such as natural language navigation, visual navigation, and visual tiling are used. These tasks test the model's ability to navigate and reason about geometric shapes, providing a comprehensive evaluation of spatial reasoning skills. Figure 2 illustrates various configurations of a navigation map under different settings of K, ranging from 2 to 7. Each example uses an emoji of a house to represent the starting point and an emoji of an office to represent the destination. These examples help visualize the route planning task and the next step prediction task as defined in the equations. Figure 3 illustrates an example of visual tiling involving a rectangle with masked polyomino pieces. The task requires selecting the appropriate polyomino variant to fit within the rectangle. The figure does not show the variants of the polyomino pieces, including their rotations and reflections. Visualization of thought, VOT, prompting is introduced to enhance the spatial reasoning capabilities of large language models, LLMs. This method involves visualizing the state after each reasoning step, generating interleaved reasoning traces and visualizations. The mathematical framework uses p-theta to denote a pre-trained language model with parameters theta, where x, y, and z represent language sequences, and b represents visualization sequences in text form. The concept of state tracking is introduced, where the state SI is defined as a combination of the input x, the sequence of thoughts Z1 to Z, and the sequence of visualizations V1 to 6-1. Visualization 6 is generated as a mental image of the internal state Si after each reasoning step Z, and the subsequent state Si plus 1 is derived from Si and 6, reflecting spatio-temporal causality and enhancing the spatial reasoning capabilities of LLMs. Figure 4 illustrates examples of visualization of thought, VOT, prompting in 3 distinct tasks. In these tasks, the large language model, LLM, generates 2D grids to serve as mental images. These grids are created to visualize the state after each reasoning step, forming an interleaved sequence of reasoning traces and visualizations. This approach allows for the tracking of the state over time, enhancing the model's spatial reasoning capabilities. Full responses and additional details can be found in Appendix B. In this experiment, the authors utilized GPT-4 and GPT-4 vision models via the Azure OpenAI API. These models were set with a temperature of 0 and top P of 1, employing zero-shot prompting. The experiments were conducted under various settings including GPT-4 COT, GPT-4 without visualization, GPT-4 VOT, and GPT-4 VCOT, each designed to handle different tasks involving both visual and language inputs. The datasets used included 203 by 3 maps for natural language navigation, 496 navigation maps, and 796 QA instances for visual tiling tasks. Metrics such as accuracy and completing rate were used to evaluate the performance of these models. The results indicated that GPT-4 VOT significantly outperformed other settings, highlighting the importance of visual state tracking in complex tasks. The analysis focuses on 3 main questions regarding visual state tracking, VOT, in large language models, LLMs. Firstly, do different prompting methods result in varying visual state tracking behaviors? The study found that GPT-4 COT demonstrated a noticeable tracking rate across tasks, except for route planning, indicating LLM's inherent capability in visual state tracking when spatio-temporal simulation is integral to reasoning. However, the behavior is sensitive to prompts, with explicit prompting improving visual tracking rates and overall performance. Secondly, how do visualizations enhance final answers? The evaluation of spatial visualization and understanding capabilities revealed that while LLMs show promising multi-hop visualization adhering to spatial constraints, significant enhancements are needed for accurate state visualization. Lastly, can VOT benefit less powerful language models? Experiments across various model sizes showed that VOT offers a scaling advantage, significantly enhancing performance in larger models, while less capable models tend to rely on random guessing, especially in spatial reasoning tasks. Table 1 presents the performance metrics of various GPT-4/4v settings across different tasks. The data highlights that GPT-4 VOT significantly outperforms other configurations, particularly in tasks requiring visual state tracking. This improvement is evident in metrics such as completing rate and success rate, especially in route planning tasks. The table also underlines the statistical significance of these differences, with p-values less than 0.05 indicating a strong performance advantage for GPT-4 VOT over other models. Figure 5 illustrates the tracking rates of various GPT-4 settings across multiple tasks. It highlights the significant differences in complete tracking rates, where GPT-4 COT shows high tracking across almost all tasks except route planning. The figure also presents partial tracking rates, indicating at least one visualization before final answer generation. Additionally, it demonstrates how visual state tracking behavior varies with different prompts, emphasizing the importance of explicit visualization prompts for improved tracking and performance. Table 2 presents the evaluation of spatial visualization and understanding capabilities in visual navigation and visual tiling tasks. It highlights the compliance and accuracy rates for both tasks, indicating areas where LLMs need improvement. The table also shows the spatial understanding accuracy, which is relatively high, contributing to better groundedness and performance. Table 3 presents the performance of visualization of thought, VOT, in GPT 3.5 and Llama 3 models across various tasks. Notably, Llama 3-70B VOT significantly outperforms the baseline in most tasks, indicating a scaling advantage with more advanced models. Conversely, GPT 3.5 COT often resorts to random guessing, particularly in spatial reasoning tasks, leading to token exhaustion. However, GPT 3.5 VOT effectively reduces these random guesses, demonstrating its efficacy in minimizing unpredictability. This table highlights the potential of VOT to enhance performance, especially in larger models, while also revealing the limitations of less capable models in sustaining reliable reasoning processes. In the NLP domain, spatial reasoning primarily focuses on semantic representation, spatial information extraction, and learning and reasoning. Recent advancements have explored spatial reasoning within the context of large language models, LLMs. To enhance multi-hop spatial reasoning skills, language models have been pre-trained with synthetic datasets, and various datasets covering 2D and 3D spatial relations have been developed. Some works have adopted in-context learning to convert spatial information into logic forms. Regarding world models of LLMs, there is ongoing debate about their ability to learn internal models from ungrounded forms. Some studies have proposed grounding LLMs in the physical world and leveraging them to predict subsequent states through action simulation. The study introduces visualization of thought prompting, VOT, which enhances the spatial reasoning capabilities of large language models, LLMs. VOT enables LLMs to outperform current state-of-the-art multimodal large language models, MLLMs, in visual tasks. The authors plan to further investigate how VOT can be applied to MLLMs to improve their spatial awareness. Future work will also focus on automatic data augmentation and developing generalized internal representations of mental images. However, the current implementation of VOT has limitations, including performance deterioration in less advanced LLMs, sensitivity to prompts, and a focus on 2D grid images. Future research should explore more diverse and complex representations to strengthen the mind's eye of LLMs. Thank you for watching.